Welcome to Unit 4.6. We are still in the process of exploring space groups, and in this unit we want to look more closely at the details. We will also learn how to read in a special book, which everyone just refers to as the International Tables. The full title is International Tables for Crystallography. And this is a large-sized 8-volume opus in which everything that is known in crystallography is collected in a compendious abstract manner. It is the definitive resource and reference work for crystallography, in particular Volume A with the title Space Group Symmetry. This is basically the crystallographer's Bible. Unfortunately, these tables are really expensive, although they are so useful. And I can tell you, as a crystallographer, you really need them. It's part of the daily work. Luckily, there is an internet resource where you also can find the most important information of this volume. What can you find in Volume A of these international tables? Well, first of all of the 17 plane groups and 230 space groups are listed systematically. Their short and full symbols are given, together with a unique group number. Furthermore, the crystal system and the respective crystallographic point group to which the space group belongs is indicated. One particular important and very useful part of these tables are the diagrams. For each of the space groups you can find diagrams in which the symmetry elements are depicted and positioned at the correct position within the unit cell. In addition to that, a so-called general position diagram is displayed, which we will get to know in a minute. Related to that are the descriptions of the symmetry operations as coordination transformations, and the specifications of the multiplicity, the so-called Wyckoff ladders, and the side symmetry. Apart from these things listed here, you can find additional information which is either of a very theoretical nature, belonging to relations within the group theory, or things related to X-ray diffraction, the method of choice to resolve the atomic structure of a crystal. As this method is not covered by our course, we will not discuss X-ray diffraction here. Okay, now finally let's have a look into these tables, this special Bible. And as a first example we have chosen the space group Pmm2. This is an overview of the 2 pages which are reserved for the entry of the space group Pmm2. And now we will consecutively explore all the information given. Let's begin with the header. Here the space group notation is depicted as short and full symbols, Pmm2. In this case these two are identical. And the unique number is given, 25. All the space groups are enumerated systematically from 1 to 230. In the middle of the header, the crystal class is specified to which this space group belongs, namely both in the notation system of Schoenflies, which is the first of the C2V point group, as well as in the system of Hermann and Mauguin, which is MM2. On the right we can find the information to which crystal system the space group belongs. And directly underneath this entry the so-called Patterson symmetry is given, which is the space group of the Patterson function. This belongs to the X-ray diffraction part, which we will not discuss here. Let's move on. Next we see 4 diagrams. 3 of them are the diagrams of the symmetry elements. They differ only in the choice of the projection plane. The most important one is always at the top left position. It shows the standard projection. Let's have a closer look. We see a projection of an orthorhombic unit cell onto the AB plane, and we see all symmetry elements as graphical symbols at their positions within the cell. These fat lines are mirror planes. So we have here horizontal mirror planes, 2 running along the edges of the cell. They are actually the same because this one is only translated by 1 unit cell along the A direction, and 1 running in the middle of the cell, all being parallel to the BC plane. Furthermore, we have also these three vertical mirror planes. These are running parallel to the AC plane. And as you already learned, two perpendicular mirror planes generate automatically a twofold axis of rotation at their line of intersection. So, at each position where two of these mirror lines meet, there is a twofold rotational axis. They run perpendicular to the AB plane, to the projection plane, and are located at every corner of the cell, at the middle of the edges, and in the center of the cell. Good. So what do we have else? Yes, this general position diagram. This is how it looks like. At first sight, it seems to be a bit complicated and confusing, but it is not. I will show you how we can generate this pattern with the help of the symmetry operations of the space group. Instead of showing you all symbols, circles, and so on at once, we will start with just one circle. This can be an atom or any other object. The only condition that has to be fulfilled is that this atom sits on a general position. We have to remember what a general position is, and we know from Unit 2.6, fractional coordinates, that this is a position that does not sit onto a symmetry element. So let's pick this atom and start with it. Now we will apply stepwise the symmetry operations of the space group. This means we will overlay this general position diagram with a diagram of the symmetry elements. And thereby we will see how this circle will be transformed and thereby multiplied. We will do this until no further circles will be generated through the symmetry element framework. First we can choose this circle. And now we apply this vertical mirror plane. A reflection at this mirror leads to a second circle over here. Now we can apply this horizontal mirror plane, and this reflection leads to these four circles. So let's further complete the symmetry element framework and take, for instance, one of these twofold rotational axes. What will happen? Of course, this will add no more circles to this diagram. The circles will be mapped onto themselves. And what about this twofold axis of rotation? Well, this circle will be transformed over here. And this one over here, far away from our initial chosen unit cell, and this will therefore not be further considered. That's also valid for the remaining circles. We now can apply these remaining twofold axes. Applying this twofold axis on this circle, this axis also on that circle, and so on. Finally, we will come to this pattern. So it looks quite complete, apart from the missing plus signs and commas. Starting from this configuration, we could have also chosen these mirror planes to complete the pattern. Because we can think of this general position diagram as a diagram in which the objects were floating around by applying the symmetry elements, I also call it sometimes the orbit of an object on a general position. However, this term is not very common. Now only two things are left. First, the plus signs. They mean that the circles are located along the C direction somewhere above the height of the projection plane. And as all circles carry such a plus sign, this means only that any of the symmetry operations do not change the height of these circles along the C direction. Finally, there are these commas. These commas come into play when not only completely symmetrical objects are considered, but objects that lack any kind of mirror symmetry. These objects are called chiral objects. These are objects which have non-superimposable mirror images, or which builds a pair of an image and the respective mirror image when applying a reflection. So here, if we choose this circle, and if this would be a chiral object, and we apply this reflection, then a mirror image is generated on this location. And if we now apply, for instance, this reflection, the mirror image is reflected again and the original image is generated at this position, and so on. Okay, so far a first view on the international tables. In the next units, we will explain the remaining things of this space group and will have a look at other space groups as well.